Dark openings are at the focal point of cosmic systems, and those are commonly immense dark openings, millions or billions of times the mass of the Sun. All through the years, physicists have relied upon a mix of speculations like general relativity, quantum mechanics, and the Standard Model to unlock the secrets of our universe. These speculations have made sense of enormous peculiarities, shedding light on how heavenly bodies act and the unpredictable nature of particles at the smallest scales. Without theories guiding us, there would be so many questions out there in the universe that would go unanswered. However, consider the possibility that we've been mixed up this whole time. Brian Greene has at long last ended his silence and said that all cutting-edge theories are off base and that we're living inside a dark opening. Join us as we unravel what Brian Greene was discussing 0.4 quite a while back, turning around one another, going close to the speed of light, banging into each other, and making a tsunami in the texture of space. This discovery might potentially change all that we've ever known about our reality. In the realm of hypothetical physics, few voices carry as much weight as that of Brian Greene. No one can deny his remarkable contributions to the field, especially in the realm of string theory. His depth of knowledge, deliberate focus, and ability to convey complex ideas to both specialists and the general public have established him as a leading expert in scientific circles. Greene's skill extends far beyond his striking research accomplishments. He has a remarkable talent for unraveling the mysteries of the universe through his books, lectures, and media appearances. Through his top-rated works like The Elegant Universe and The Fabric of the Cosmos, he has effectively bridged the gap between the obscure world of hypothetical physics and the interest of the broader public. His unique ability to distill complex ideas into accessible narratives for everyone has empowered countless individuals to engage with significant scientific concepts. In this way, he has also been responsible for growing the scientific community overall. Yet, it's Greene's academic background and professional achievements that solidify his position of authority. As a professor of physics and mathematics at Columbia University, he has guided and inspired numerous aspiring physicists, fostering a new generation of scientific thinkers. His research contributions in string theory, a framework aiming to unify the fundamental forces of nature, have propelled the field forward and earned him widespread recognition from peers and experts worldwide. So, when a man like this says something, the world listens. He claims that all the advanced theories we have consistently looked to for answers are completely off base. We're not just inside our local planetary group, we're inside a dark opening. Everything we've known about our world is false, and this whole time we've been inside a dark opening ourselves. But how could that be? Could current theories be this wrong? The idea that our universe might exist inside a dark opening has been explored by scientists for some time now. Over the years, several theories and ideas have emerged to propose how our universe could be connected to or originated from dark openings. One idea put forward by some physicists is that each dark opening might give rise to a new universe. This idea is based on the concept of tor-ion, which proposes that inside each dark opening, another universe is created. From this perspective, dark openings act as vast passages leading to the birth of new universes within them. Another idea suggests that our visible universe is inside a dark opening, which itself exists as part of a larger parent universe or multiverse. In this view, dark openings serve as portals to different regions or dimensions of spacetime, including various universes or realities. The singularity, the infinitely dense core of a dark opening, is also seen as a potential source for the birth of new universes. Some experts suggest that the singularity inside each dark opening could have resulted in our own universe. This idea draws parallels between the initial state of our universe, commonly referred to as a singularity, and the concept of black hole singularities. Another interesting theory is that our universe originated from a dark opening that resides inside another universe. According to this theory, when a dark opening forms through the collapse of a dying star, a parallel universe is simultaneously born through a white opening located on the other side of a hypothetical wormhole. This idea connects the formation of dark openings to the creation of new universes. But that's not all. Some theories suggest that our universe could exist inside a higher dimensional dark opening. This perspective proposes that our universe began as a singularity, a point of infinite temperature and density, similar to how the scientific community describes dark openings. The theory suggests that our universe is trapped inside the event horizon of a four-dimensional dark opening. This would mean that we couldn't recognize that we're inside a dark opening no matter how hard we try. However, this theory contradicts everything we know about how our own universe works, things that we've currently examined and proven with modern physics. Current physics includes a range of theories that aim to explain the fundamental nature of the universe, from its largest structures to its smallest constituents. These theories have been developed through rigorous scientific investigations and have provided remarkable insights into the workings of the universe. At the core of modern physics lies the framework of quantum mechanics, which describes the behavior of particles at the atomic and subatomic scales. It introduced a new way away from classical physics, which relied on strict laws and precise measurements, by revealing the nature of the microscopic world. One of the key concepts in quantum mechanics is wave-particle duality. It reveals that particles like electrons or photons can exhibit both wave-like and particle-like properties. This means that they can act as discrete particles with distinct positions and momenta, but they can also display wave-like characteristics such as interference and diffraction patterns. This duality is captured by the mathematical formulation of quantum mechanics, which uses wave functions to describe the probability distribution of finding a particle in different states. Another notable aspect of quantum mechanics is superposition. According to this principle, particles can exist in multiple states simultaneously, a phenomenon not observed in classical physics. For instance, an electron can be in a superposition of spin-up and spin-down states, meaning it exists in both states at the same time until a measurement is made, collapsing the wave function into a definite state. Quantum mechanics has revolutionized our understanding of the microscopic world, paving the way for technological advancements such as lasers and nuclear power, which rely on the principles of quantum mechanics. So, quantum mechanics explains the world as we know it from a microscopic view, the building blocks of life. Since their discovery, we have known that everything functions in a certain way, the way it should be the truth. But that's not all. There are aspects of various theories that have consistently explained how our Earth is and how the world truly works. General relativity, for example, describes gravity as the curvature of spacetime caused by matter and energy. It provides a mathematical framework for understanding the behavior of massive objects, including everything from planets and stars to galaxies. The theory successfully explains a range of phenomena, including the precession of Mercury's orbit, the gravitational lensing of light, and the expansion of the universe. However, general relativity breaks down in extreme conditions, such as at the center of dark openings or during the early moments of the Big Bang, requiring a more complete theory of gravity. But the standard model of particle physics takes things further. This is a highly successful theory that provides a comprehensive framework for understanding the fundamental particles and forces that make up the universe. It includes three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Each of these plays a crucial role in how our universe works. The electromagnetic force is responsible for interactions between charged particles like electrons and protons. On the other hand, the weak nuclear force is involved in processes such as radioactive decay and certain types of nuclear reactions. The discovery of the W and Z bosons, carriers of the weak force, has provided strong experimental evidence for the validity of the electroweak theory within the standard model. The strong nuclear force is responsible for holding atomic nuclei together, mediating the interactions between quarks, the fundamental particles that make up protons and neutrons, through the exchange of gluons. Quantum chromodynamics, a branch of the standard model, describes the behavior of the strong force and has been successfully tested in experiments. The theories we are discussing here aren't just theories. They have been proven time and time again to be the real deal. In addition, the standard model even predicted the existence of the Higgs boson, a particle associated with the Higgs field. The Higgs field is thought to be responsible for giving particles their mass through interactions with the field. In 2012, experiments conducted at the Large Hadron Collider confirmed the existence of the Higgs boson, providing even further validation for the standard model. However, despite its successes, the standard model still has its limitations. One significant limitation is its inability to account for the presence of dark matter and dark energy, which are believed to make up a substantial portion of the universe. Dark matter, a form of matter that does not interact with light or other electromagnetic radiation, is inferred from its gravitational effects on visible matter. Dark energy, on the other hand, is hypothesized to explain the observed accelerated expansion of the universe. Understanding the nature of dark matter and dark energy remains an active area of research in the world of science and is also one of the central building blocks of dark openings. But that's not where the challenges stop. There's also the issue of trying to unify the gravitational force with the other fundamental forces. The Standard Model does not include a description of gravity, which is instead described by general relativity, a separate theory. So perhaps Brian Greene has a point. His expertise lies in exploring the fundamental nature of the universe, seeking a unified theory that includes all the forces and particles within a single framework. One of Greene's notable contributions is his work on mirror symmetry, a concept within superstring theory. Mirror symmetry establishes a significant connection between two seemingly distinct calibi Y.